Good morning, everyone. This is Jim Chastain with EasyPower. Welcome to our Tuesday refresher. Today we're going to be talking about the top 10 mistakes we've encountered or we continue to encounter in arc flash studies. And we scheduled this for 30 minutes this morning, so we're probably only going to cover half the list. And even at that, we may run long. So welcome to our session. And we may not be able to answer questions online, but by all means, if you have questions, submit them to using the question box and the control box from the webinar, and we'll either get to them as we can or answer them via email. Each year we're involved, we conduct a dozen or so arc flash workshops and review a couple dozen initial studies from different tool users, and we find the mistakes often fall into some generalized categories. And so I've made a list of what the most common mistakes are, and this is where we're headed now. So mistake number one is what I refer to as arc flash paradox. And it actually affected me in my early days with EasyPower. I received a call from an electrician in Oklahoma who had just purchased the tools. He said, "Jim, I have a problem with your tools." I said, "What's that?" He said, "Well, I need to label the above ground electrical distribution system in an oil field here, and I just have a question. I have a problem. I think your tools have a bug in them." Well, so tell me about it. So we got online in a GoToMeeting session, and as we did so, he described his one-line diagram. He said, first put a utility icon and then a two-winding transformer in the one line. My incoming voltage is 12.8 kV, so we enter that. He said on the secondary side of the transformer, just put a bus. The distribution system is at 480, and then expand that bus itself out to about half the width of the screen, and then drop a cable on each end of that bus. So I'm doing this as we're talking. And he says, put a plain bus at the end of each cable. Now, the reason I like this example is that he had one protective device in his system, and it was a fuse in the utility cutout switch. So we put that up here in the incoming utility bus. He said this first cable is 50 feet long, THWN 350 kcmil, and we can copy and paste that into the second cable. He said, as I open up the dialog box, the second cable is actually 1,000 feet long, so we type in 1,000 feet. He said, the transformer, I've looked at the nameplate, it's 1,000 kVA, oil-filled. The impedance is 5.75%, so the tool calculates the other parameters that are necessary for analysis. And he says, I've looked at the label on the fuse in the utility switch. It's an AB chance fuse link Model T. For some reason I remember Model T, and it was a size 10. So we've completed his one-line diagram, and he said, okay, I go into short circuit focus, and I look at the half cycle bolted fault currents. These all look pretty normal, so now I'm ready to do my instant energy calculations using this little guy at the top. And now we see we have three different values. At this bus 2, which is the transformer secondary, I see that the arc flash boundary is 28 inches. The incident energy is 2.3 calories at a working distance of 18 inches, so I know what PPE I need to wear there. We go down to bus 3. The arc flash boundary is 29.2 inches. Incident energy is 2.4 calories per square centimeter at a working distance of 18 inches. So I know what PPE I need to wear there. Now when I go down to bus 4, the incident energy has almost doubled. The arc flash boundary has doubled. And now you're telling me I need to put on more PPE to work on this bus hot. He says, what's wrong with your tools? I said, I'm not following you. What's your question? He says, well, I've been an electrician for 25 years. And anyone that works in electricity knows the farther away you get from your utility source, the lower the energy is going to be. So why does your tool say the energy goes up? Well, my response to him was, well, Vern, I've been an electrical engineer for 25 years, and frankly, I agree with you. I don't understand why the energy goes up. It seems to defy Ohm's law. Well, the moral of the story, and the next step that we took, was to utilize this icon at the top center of the screen called a range for arc flash. And what that lets us do is see a spreadsheet that shows how the calculations were made. So if we isolate this first bus, we can see that the voltage on the bus is 480 volts. The protective device in the system is FS1, the fuse. The way we define the bus, the air gap is 32 millimeters, and we already knew the bolted fault current was 20,915 amps. According to the IEEE model, the maximum current an arc will draw under those conditions is 9,897 amps. According to the manufacturer's datasheet for that fuse, the fuse will trip, subjected to that much current in the secondary, the fuse will trip in 72 milliseconds. You put all that information into the IEEE equation, and you come up with a 28-inch arc flash boundary and a 2.3 calories per square centimeter instant energy. Okay, let's go down and look at bus 3. So we isolate that, double click on it. We see we have 480 volts, the same fuse as a protective device. The air gap is still 32 millimeters. Here the bolted fault current is 17,878. According to the IEEE model, the maximum current an arc will draw under those conditions is 8,684 amps. According to the manufacturer's datasheet, that fuse will blow in 88 milliseconds in the primary side of the transformer if that much current's in the secondary side. You put that information into the IEEE model, we get an arc flash boundary of 29.2 inches, instant energy of 2.4 calories per square centimeter at a working distance of 18 inches. Okay, that makes sense. Now let's go to bus 4. We isolate on it, and now we see same voltage, 480 volts, the same fuse as a protective device, the same air gap. Now our bolted fault current is 4,351 amps. According to the IEEE model, the maximum current an arc will draw is 2,676. According to the datasheet for that fuse will open in just over 3/4 of a second. Well, that means if I wear the same PPE that I wore when I was working on the secondary of the transformer, and I'm working on bus 4, and I accidentally initiate an arcing flash, that explosion will last 10 times longer than it would have lasted had I been working on the transformer secondary. So consequently, there's much more energy released, and the PPE that I had on would not be adequate to protect me in that situation. And both of us simultaneously said, duh, I get it. Time is everything. We're talking about arc flash. So the arc flash paradox is, roughly speaking, within the same system, you can have a bus which will have higher current and calculate higher arc flash energy, and other buses which will have lower current and calculate higher arc flash energy. The bottom line is it all depends on the time to quench the arc. So that's probably the most frequently least understood aspect of the whole arc flash study that I encounter time after time after time. So mistake number 2, haste makes waste and frankly bad models. I think there's an intention or enthusiasm to start too large once they start the process of drawing the one line, is to draw it all at one time and then deal with the consequences. And so what this does, especially if they don't understand the mechanics of either the EasyPower tools they're using or frankly the arc flash paradox, it can cause a host of errors, and fixing the errors may require actually going back and collecting more data at the site, which will incur wasted time and a need to kind of redo, frankly, the one line multiple times. Now, the first order of events when you're conducting an arc flash study is to complete a short circuit study. And that means that we need to know the voltages and the impedance. The short circuit study is focused on analyzing the worst case current, short circuit current that will occur in our system, and secondarily, will the equipment survive and operate properly once it's subjected to that initial surge of fault current. So frequently people will start with, even a one-line diagram as simple as this can be overwhelming if you don't know what you're doing or have not looked into the details of the mechanics. What I recommend is start with a very simplified one-line diagram from the utility source through however many layers of either different voltage conversion or protective devices down to a typical load that you need to label, and make sure that you understand what data needs to be used in the tools to produce this report. If you go through and try to complete the study or utilize the tools, you'll find messages such as this, which indicates, well, there's some incomplete data. Do you want to see an error report? And so it will give me a list of the specific elements that don't have data and flag them on the one-line diagram. Now, obviously, this is much easier to deal with if I'm working on a very simplified one line, as opposed to having drawn the whole radial system to begin with. Now, the second part of this mistake and the second step in an arc flash is determine the trip settings for protective devices. If I have conveniently collected that data as I do my data collection on the other parameters in the system, then I can save myself a second or third trip to the site to collect more data. But if I haven't, and I've drawn the one-line diagram without these settings, I'm going to have another round of errors. And if I have a very extensive one line, I can find that as I fix the errors at the bottom, they start to matriculate up and interact with each other. Again, what I suggest is on my simple one-line diagram, once I've completed the short circuit part and everything looks normal, then I'm ready to go into and utilize a little arc flash Burning Man symbol on the top row up here. But what I see is there's no results. There's blue indications on the buses, which just means they were analyzed or they attempted to produce results. Again, I want to use this little icon at the top, arrange for arc flash, and as I do, I see that the indication on my one line is no valid trip device. And that's, like I say, the second most common mistake I see over and over is that people were in a rush to draw the one line without really totally understanding what I needed from the equipment in the field. So I take a step back and recommend, even in my simplified one-line diagram, to put in a fuse just like I did in that first example and put it up in my utility bus and then parameterizing it. And I personally continue to use the AB chance because I know it's if I use these elements or these parameters, it gets I don't have any mistakes. It gets thoroughly used. So now when I'm ready to go back and do my instant energy calculations, I get results. And if I look at my arrange for arc flash report, sure enough, it shows answers or instant energy at each bus. But what's even more telling, if I look a little closer, the upstream trip device, everything's referring to the fuse, which tells me, okay, I must have connections throughout my bus down to the load, but I'm missing details on every one of the protective devices. Now, to dig deeper into this, each element in the system has a dialog box. Each element, not just the protective devices, not just the motors, not just the cables. Every bus has a data box as well. And it's important to understand as I'm filling this in, and for instance, in the breaker dialog box, that there's several tabs across the center that need to be dealt with. And depending upon how complex the system or how complex the components I'm using, I may need something more than just the manufacturer's data sheet and part number or name and part number. I may need to know the ground trip settings, fuse settings, or even some advanced feature parameters. Nevertheless, as the tool tries to help me as I go through this and indicate things like this red exclamation point, in this case on the phase trip tab, and if that's not completed, I will fail to get results, at least that I think I deserve when I continue to get into the instant energy. So again, haste makes bad models. Understanding the elements, minimizing multiple trips to the data site. I recommend that you download and read Practical Solution Guide to Arc Flash Hazards, which is available in the handout section of this webinar. And it goes through the steps in a logical order to prevent these errors from occurring. Third most popular error, and that is to just disregard the fact that bus types and other parameters in the bus have a significant bearing on the satisfactory completion of my study. The Brown Book, which is the appellation for IEEE 399, describes what's required for a short circuit study and how to conduct it. And the things that we're looking for is a worst case fault current, the effects on interrupting devices and other system elements. We want to compare the manufacturer's rating with the worst case current that's going to occur in our system, and then create a report, at least for posterity, that shows these have been examined at some point in time. EasyPower will do this comparison for us if we've entered the data. Take that one step further, and we talk about the requirements of IEEE 1584 arc flash models. Requires specifics on the air gap, and the air gap will vary based upon the bus type and the voltage, and there are default values. And so if you'll see, we'll look in the EasyPower library, these gaps are defined at 480 volts as 32 millimeters for an other type of panel, 25 millimeters for a panel, and 12 millimeters for a conductor connection. The point being that all buses are not created equal. Now, with the upcoming release of IEEE 1584 2018, we're presented with 5 different categories of buses, all of which can make a difference on our arc flash instant energy calculations. So you'll see that different voltages and different categories of bus will dictate different air gaps. Then the bus orientation and termination will play a part in how the energy is radiated. And finally, the worker's physical position with respect to the bus could amplify radiated heat in the case of an inadvertent arc flash. So all these should be taken into account in a study, and as I'm building the one-line diagram, I need to make these decisions. I can set up the tools to have default settings pre-configured, so as I build the one line, there's a certain number that I've automatically filled in, but there are certain areas where it should receive more scrutiny, and the need for accuracy actually expands. So let me kind of jump into an example and show you what I'm talking about. And I haven't talked about it, but we're going to use, we're going to have a sneak peek at the upcoming version of EasyPower that's going to accommodate the 2018 1584 update. So here's a typical one-line diagram that may or may not be a first effort. And as I go in and so I received this from a customer who was looking for some feedback. So the first thing we do is look at our short circuit results, fault all the buses, and we get a clean one-line diagram with current all flowing the right way, and nothing seems to be afoot. The function of equipment duty is this little icon here at the top on the second row, which will display our report. And we're seeing some indications of problems here without any numbers, except in the case of this load bank, which is indicating it's 140% over-dutied. Well, that's disconcerting. So I'm going to go back to my database edit, and the question is, how do we head off some of these mistakes before we get into analysis? Built into EasyPower is a facility or a utility called Database Browser. If I go down under File, Database, Browser, it gives me some really nice parameters about the one line I've drawn. For instance, in this case, we have a total of 26 buses or nodes. I can go up to my equipment pull down and look at these elements as a group. So first of all, I want to look at buses, and right away I see my one-line diagram does not have any buses with their rated ampacity indicated or their bracing. These are the elements that are used to indicate whether or not we're over-dutied. And then if I go a step further, I can see that I haven't made any differentiation between what type of bus. So obviously I'm missing a lot of data. Now, when I go back to my other equipment I want to look at would be my low voltage breakers. Again, he's got all of his breakers in here. He or she has all of her breakers in here, but there's no details on the specifics, and so consequently nothing's going to be accurate as far as my calculations. So right there I can tell my one-line diagram is not adequate. I have really no business jumping into arc flash analysis. But to take it a step further, if I go to short circuit focus, I fault all the buses and look at my half cycle current. Sure enough, if I go and look at the range for arc flash, I can see that in every case the fuse is the protective device. And if I come up and look at this, quite literally, and I don't recall whether I put this in or whether the client put this in, but he used my AB chance fuse, and without that we would have had no protective device found. All right, so yeah, I'll take one more step here. When I'm setting up a bus, I open up the dialog box. On the specification tab, I have the ability to indicate what type of bus this is. By default, other is what is brought up, at least the way I'm set up. And in many of these cases, we have switchgear or panels, and there is an implication or a factor that affects my calculations. Likewise, I should have had something in my ratings and my bracing and the material, all of which could be impinge upon the accuracy of my results. All right, so let's not beat that up anymore, and we'll come back to this in a second. So, and this, like I say, should be dealt with in building the model because that's the time I'm entering the data. Number 4, some very common mistakes when we're talking about high voltage or medium voltage systems, and frankly the most common is using the infinite source utility. There was a day and time when it was considered the best worst case, and if we approached the utility company to know what available short circuit current was being presented to my facility, they would give me the infinite, or they would say use infinite source, because this does affect or result in the biggest stress in the system in terms of higher current. And that's one of the things we're looking for during the short circuit study. On the other hand, the infinite source may not be the best case for calculating instant energy, or the most conservative case, and frequently the real data, that is the most typical short circuit current available at any given time, would be better for calculating arc flash. If the company doesn't, or if the utility company cannot or does not make that information available, one way to approach that lack of information is to use a scenario that calculates at 50% of the available short circuit current and see what the results are and if that makes a worst case situation. This example is described in the handout handout section I've provided in the document called Data Collection for Arc Flash Study. And what this does is present a comparison between the infinite utility being supplied to my system and an actual utility that's supplied over a 2-mile tension line, high tension line to my plant. Everything below HV1 and HV2 is identical. And so what we see under an infinite bus, the available short circuit current at my plant is 20,600 amps, whereas if I have taken the realistic approach and using actual utility data, the maximum worst case current is 16,700. Now, as we then calculate instant energy, and again, this is described in the handout, I see that my instant energy for the realistic fault current is 52 calories. The infinite bus ends up at less than 32 calories. So the more conservative results is actually the lower current. And again, this is a little bit counterintuitive, and that's why I continually run into the arc flash paradox. But this is a case, and frequently it is the case, that a more conservative arc flash result will occur with the realistic fault current. So again, I encourage you to duplicate this result or duplicate the example that you find in the handout. Now, the other question that comes up is if you're using the infinite source, did you even call the utility company? Now, again, frequently they may be reluctant to provide the data. If you explain what you're doing as far as an arc flash study, they may be a little bit more helpful. The tool actually allows us to take data in 3 or 4 different formats, and there is a discussion in both the data collection notes and in the practical solutions guide handout for how to deal with or how to estimate utility short circuit current if the company doesn't have it available. And again, if you're having to do some estimates, you may want to run multiple scenarios to see where your sensitivity or where your worst case might be based upon what even the estimates that you're coming up with. And then the second part of this mistake, which is the medium voltage section of my oneline, if the 480 switchgear that's being supplied by a substation has the same instant energy, and we see this down to the second and third most significant digit, then you probably have made a mistake. The point being, different loads on adjacent panel boards or adjacent switchgear, different transformer impedances if we're using different substations, different cable routing, all will affect what the instant energy on that switchgear and the 480 distribution system will be at the top. And so if you have exactly the same number, then you need to go back and check your work. Again, we run into that more often than you think. Number 5, this used to be called, or is called, the low voltage exception. And in the original version of 1584, it had the verbiage that less than 240 volts supplied by a 125 kV transformer or less can be ignored. And it's true, there's some people think it's been removed from the standard. Turns out the verbiage was part of NFPA 70E and it's been removed, but that's not directing the calculations. In 1584, the 2002 version, the exception is still there. When we see, or what appears to be the release coming up on the 2018 version, the low voltage exception is still there, but it's been modified. And so the verbiage is sustainable arcs are possible, but are less likely in three-phase systems at 240 volts or less with an available short circuit current below 2000 amps. We will talk more about this in subsequent webinars, but for now, I just want to run through a real quick example that touches on this, but it goes back and compares the differences that we see on the different categories of buses. So bear with me briefly, but again, part of this is a preview of the EasyPower update, which is coming as soon as the IEEE 1584 model is released. All right, so what I've described here is a bus system at both 480 volts or distribution system at 480 and 240, and we've described half a dozen different types of buses. By default, our bus type, in this case is a switchboard, when we go to arc flash hazards, we're using the default library for the electrode configuration. And that ends up being a vertical orientation in a closed box. If I go to defining my custom description of this, again, I have a switchboard that's copper. I have my rating and bracing. If I look at the electrode configuration, I'm specifying it as vertical in a closed box, VCB. We can also have vertical terminating it into a barrier, and this they found amplifies the radiation, heat radiation. So I've specified vertical in a closed box terminated in a barrier. Likewise, horizontal orientation tests have shown that we have increased results as far as radiated energy when we have termination into a barrier or if the bus work is positioned horizontally, and then the incident energy is much less if we have open air. So I've got all these described and set up in my one-line diagram. I'm going to just select this set of buses. We're going to go into short circuit focus, look at half cycle current, and fault the buses. So all my half cycle currents identical. All the breakers are set up to give me instant energy of somewhere in the acceptable range. And you notice here, and frankly what we're using, I'm going up to my short circuit options, arc flash hazard. I'm right now using the standard 2002 version of 1584. And what that shows us is there's a little bit of a difference when I'm using barrier termination, but the horizontal termination was exactly the same, and my open air didn't matter whether I was orienting the bus horizontally or vertically. So now if I go back to my short circuit options and invoke the updated version of 1584, we can see we have quite a bit of difference. I'm going to fault these buses again. Here we have the default and the vertical box are the same values. The vertical terminating into a barrier looks like it's about a 10 to 15% increase in radiation. Horizontal makes a fairly significant, looks like it's 80% over a vertical orientation. Open air is less, but open air horizontal is about 50% worse than the vertical orientation. Now if I go back to our arrange for arc flash, which I am want to do, I can see that the tool now shows me the electrode configuration and the dimensions that are being used. Now you may have noticed I just used the default dimensions for my enclosures. We'll get into the more details on this when 1584 is actually released. But I can see now that at least there's reasons to be considering this based upon whether or not I'm encroaching on threshold levels. Speaking of which, let's go down and look at the 240 volt system. We have the same construction as far as the bus work orientation. We're going to fault these buses and look at the arc flash instant energy. And again, right now we're on 2018 version. Let's take this back to 2002. And the point I want to make here, this is the low voltage. What we're showing, or what we had, we're right above the 2000 amp level. All right, so we need to really take a look at what the instant energy is. And under 2002 calculations, we have some fairly elevated instant energy, which again doesn't make that much sense in a low voltage system. If we now go back and apply the calculation methods for 2018, we see that we get more realistic, less conservative results for the enclosed vertical sections. We're having, I'd be concerned about this particular calculation in my horizontal orientation, and in both the open air and horizontal in a box, we have elevated instant energy. Again, we'll talk more about this when we get into the details of the 1584 release, but I just wanted to give you a sneak peek at how much the calculations are affected between the old standard and the new standard in some cases. And the low voltage is, in my mind, it's even a little bit more vague than it used to be now that they've eliminated the 125 kVA discussion. And consequently, I think we need to look a little bit more closely at what currents are being involved and how that affects our particular system. All right, so hopefully you got something out of that. That was kind of fun for me. And again, these are part of the bus data arc flash hazard tab. We can stay with the default setting, which will give us essentially a vertical closed box, or we can detail what our particular system is. Okay, so we're halfway through the list. The arc flash paradox, I think, is important to understand. I encourage people to go through that example individually. I do encourage a little bit more time before you just start drawing. In fact, I encourage playing with the tools before you even do data collection to make sure you have a good handle on the important elements of the calculations. I think it is important to look at what the bus orientation is, because now going forward, it's going to have a greater impact on what the calculation results are. I think be careful in considering utility calculations, and we need to I think, have more conversations on the low voltage. I encourage folks, if you can't download the documents that I have in the handout section of this webinar, they're available on the resources page of EasyPower.com, or contact sales@easypower.com and said, hey, Jim said I could get some documents. Let them know what you need. Thank you for attending today. I encourage you to check with the website frequently. We have updates on the software. As soon as we're able to release a new version, it will be announced. We are posting new training dates for next year and locations. And there's always the latest information on upcoming webinars. I encourage folks to pay attention to the newsletters we send out. It's not typical spam, and most often we only send it out when there's vital information I think that's of interest to our customer base. I did want to remind folks, with current maintenance on the tool suite, you have virtually unlimited access to tech support via phone or email. And frequently, more and more people are taking advantage of our Power Start, which is a free orientation session for new tool owners. And the idea is to get you up and running on your first one-line project and better able to access and utilize tech support to answer questions. So thank you for attending, and we'll be completing the list in 2 weeks. Look forward to talking to you then. Have a good day.